Michael is graduated from Notre Dame with his PhD. Claudio, who's online, was his supervisor. Then did the strangest postdoc ever in Queens for 1 year, completely locked down during COVID, and I don't think ever entered the math department, or it was never required to enter the math department. Everything was virtual. And since then, he's been a postdoc at Minnesota. He's going to tell us about local cohomology, D modules, and Schubert varieties. Michael.
Thank you very much for the introduction, Greg, and the invitation to speak from the organizers. So I want to tell you a bit about local cohomology, and my cursor isn't working. And when I say local cohomology, I mean a very specific thing. I'm usually talking about local cohomology of the polynomial ring over the complex numbers with support in some ideal. Right? And it turns out that these guys aren't just modules over the polynomial ring. They have much deeper structure on them, namely that of a mixed Hodge module, which is some special bifiltered category of D modules. They have a Hodge filtration and a weight filtration. And somehow these filtrations detect and measure the singularities of I. And there's been a recent explosion in the theory, especially in the case of complete intersections. But many basic questions remain open in the case of non-complete intersections. Because, I mean, in the complete intersection case, there's only one local cohomology module. I mean, one of the problems in this theory is that it's very hard to calculate local cohomology, and there's a lack of examples. Right? On the other hand, techniques of D modules were pioneered in representation theory in the 80s and 90s, and they were interested in geometry of varieties with large groups of symmetries. And there's been a recent effort to bring these techniques to commutative algebra to study local cohomology, namely in the case of determinantal varieties. Okay. And what I want to tell you about today is a new calculation generalizing the case of determinantal varieties to that of Schubert varieties. Oh, and by the way, please, if you have a question at any time, please interrupt me. All right, so I should start from the beginning. Well, what is D? So S for me will always be polynomial ring in capital N many variables. And D is the S algebra generated by the partial derivatives of the variables. It's called the Weil algebra, subject to these commutativity relations. And these commutativity relations are what ensure D acts on S the way you think it should. So this first one is that mixed partials commute. And I taught multivariable calculus recently. They call this Clairaut's theorem in multivariable calculus. The second one says that if you move a partial I past an xi, you pick up a 1. That's the Kronecker delta. And you should think of this as the Leibniz rule. Okay. Now, again, so this is not a commutative ring. So that it's almost commutative, though, in a sense that can be made precise. So when I say D module, I mean left D module. And like I mentioned, our favorite example of a left D module is the polynomial ring itself. We can differentiate polynomials. But in fact, it's a special D module. It's simple, meaning it has no non-trivial proper submodules. It's not obvious, but it's an exercise that you could differentiate every polynomial down to a non-zero constant. And once you have a non-zero constant, you can hit it with any polynomial. Okay. Next most important example, from my point of view, is the localization of the polynomial ring at a non-constant polynomial. So this is fractions with powers of f in the denominator. And this is a D module by the quotient rule from calculus, right? If we have a power of f in the denominator, after we differentiate, we'll also have a power of f in the denominator. And this guy is never, I mean, if f is non-constant, this guy is never simple. It always has s as a proper submodule. A third important player is this guy E. I call it E because it's the injective hole of the residue field. Here are 3 other descriptions of it. as d mod the variables, or the polynomial ring in the partial. So you should think about it as the upside down polynomial ring. Okay, and this guy's important because it turns out that he's simple, and in fact he's the only simple D module supported on the origin. And so whenever you're working with homogeneous things, this guy plays a key role. Okay, here's a description of it as the top local cohomology with support in the homogeneous maximal ideal. I haven't defined local cohomology yet. I'm going to do it now. So this is more of a theorem definition. So I start with an ideal that I care about and some choice of generators of that ideal, and I create what's called the check complex. You start with S, and you map it diagonally to the direct sum of S localized at the generators. So here a polynomial G would go to G over 1, G over 1. And then on each factor, you do that again with a further localization, but you want to introduce a sign so that it's a complex. Okay, and then you repeat this process until you get to the S localized at the product of all the generators. Okay? And the qth local cohomology with support in I is the qth cohomology of this complex. And of course, you could do this for any module that any S module you care about, but today we only care about S. Okay? Why is it a D module? Well, I already told you why everyone in the complex is a D module. And it's an exercise to show that the maps are D linear, and therefore the cohomology inherits a D structure. Okay. And so here's the theorem part of the definition, is that this only depends on the ideal up to radical. It only depends on the reduced variety. Okay, so in particular, not on the choice of generators. So I could use any generating set to calculate this, in theory. And it's called local cohomology with support in I. Each one of these guys is supported inside V of I. The first example everyone sees is the case of a principal ideal where there's only two terms in the complex. And if this polynomial is non-constant, then there's only H1, SF mod S. And we see that this is indeed, everybody in here is indeed killed by a power of F. All right, so some quick two reasons why one might care. One of which is if you're interested in an invariant called the arithmetic rank. The arithmetic rank of an ideal is defined to be the minimal number of generators up to radical, or the minimal number of hypersurfaces required to cut out your variety. Okay, and since the local cohomology doesn't care about which generating set you chose up to radical, you get a lower bound on the arithmetic rank by the length, the shortest length of the possible check complex. Okay, so the highest non-vanishing local cohomology gives a lower bound, an obstruction for arithmetic rank. Okay? And so, I mean, there's many open questions about the arithmetic rank, in particular, in the case of curves in P3. The point of view I'm going to take here is that it's an invariant of singularities. And what I'm going to tell you about in the next few minutes is how it's an invariant of singularities. And before I do that, I have to tell you about some basic vanishing and non-vanishing of these gadgets. And for simplicity, I'm always going to talk about a prime ideal. Okay, so I is prime and C is the codimension of that prime. And here's a chart on what happens in each cohomological degree. So we always have vanishing below the codimension. And the codimension guy is always non-zero. This is a special module that's going to come up many times going forward. And then after that, we don't really know. There's not very many good vanishing theorems. But luckily, so n here is the number of variables always. After the number of variables, we vanish, as you might hope. So comparing that to the two examples that we know, both being complete intersections, The hypersurface case, we only have H1, the codimension, and it's because the arithmetic rank is 1. And the homogeneous maximal ideal, we only have top local cohomology, which is this guy I called E earlier. Now, once we have that, the real richness in the theory comes from looking at a deeper structure. The first layer of which is the D module structure. Okay, these guys, they satisfy a very strong finiteness property called holonomicity. And unfortunately, I'm not going to define it, but it wouldn't be illuminating if you saw the definition for the first time right now anyways. What you should really be thinking about is that these are finite length D modules. And what I mean by that is that they have a finite filtration by D submodules, and the successive quotients are simple D modules, meaning they have no non-trivial proper submodules. So in algebra class, we would call this Jordan-Holder filtration or a composition series, and we would call these the composition factors. So for example, in the case of the homogeneous maximal ideal, Hn is simple, so it has length 1. Okay. Here, it's already in the hypersurface case, it's already a highly non-trivial problem to find out the composition series. One remark is that this is the fact that Lubeznik used in '93 to show that these guys have finitely many associated primes. So to give you a taste of how the D module structure can detect a singularity, again, C is the codimension here. This HC that is never 0 always has a very special simple submodule. It's the unique simple submodule of it, and it's called the intersection cohomology module associated to I. And I'm not telling you what it is. I mean, I guess this is a definition, but figuring out what this guy is in practice is a hard problem. The name intersection cohomology module comes from an equivalence of categories between D modules and perverse sheaves, and the intersection cohomology complexes correspond to this guy. Okay. So for example, the E on the previous slide is the intersection cohomology module of the origin. All right. And so this guy has support equal to V of I, and all other simple factors of all the local cohomology modules are supported in the singular locus. Okay. In particular, if you're non-singular, then there's only one composition factor in cohomological degree C, and all other local cohomology modules vanish. Right. Now, unfortunately, the converse to this fact is not true. So if you look at I to be the twisted cubic, or the affine cone over the twisted cubic, its cohomology also satisfies this property, despite the fact that it has a cone point at the origin. Right. Here's one where the D module structure does detect the singularity. So if we look at 3x3 matrices, and we look at the ideal of 2x2 minors of the 3x3 matrix, which has codimension 4, well, this is affine cone over Segre product. It has a cone point at the origin, and the local cohomology detects the cone point. So here there's only 2 non-zero guys, H4 and H6, and we have the simple sub that we know exists, and it turns out that the quotient is E, the injective hole of the residue field. Okay, and then H6 is simple, it's equal to E. Okay, and the appearance of this guy is detecting the singularity.
Mike, there's a question in chat.
Yes.
Is there a relation or duality between the intersection cohomology here and that for the notion of intersection homology for pseudomanifolds? Is the question? Is it?
A duality theory, like maybe like a Poincare duality on the local cohomology, not that I know of. No. Other questions? So this guy's important guy. Okay, let me show you a slightly bigger example just to give you a taste of what else could happen. So here, now we're looking at 3x3 minors of a 4x4 matrix, which also has codimension 4. And here, the singular locus is defined by I2, the matrices of rank at most 1. And so we see that there's 3 non-zero local cohomology modules, and they're detecting the singularity in some subtle way. Here, by the brackets and the plus, I mean in the growth indeed group. So these are the composition factors. And we'll come back to this example from a different point of view later. So before moving on, I want to give you a smattering of some other ways that the singularity is detected, and this is maybe related to the question that was just asked in the chat. So this condition of the Cth guy being simple and all others vanish has a name in topology. It's called rational smoothness. And in particular, it means that the de Rham cohomology of the variety is the same as the intersection cohomology of the variety of Goreski-McPherson. Now, this is a cohomology theory for singular spaces that satisfies nice properties like was asked the Poincare duality. So this condition says that the de Rham cohomology of your variety, despite the fact that it's singular, satisfies Poincare duality. Here's another one I mentioned in the hypersurface case, that it's a non-trivial problem to find the composition series, and here's maybe a taste of why, is you can look at this natural filtration on the localization given by D submodules generated by negative powers. And so this is an increasing filtration, and by holonomicity, it must stabilize. It must be a finite filtration. And I'm not going to define Bernstein-Sato polynomial, but it turns out that the only places that there can be jumps are at roots of the Bernstein-Sato polynomial. And maybe you've heard of it, maybe you haven't, but the roots of the Bernstein-Sato polynomial have deep connections to singularities in algebraic geometry and in topology. Next one goes by the second vanishing theorem for local cohomology, which I paraphrase a consequence of. And the second vanishing theorem is some relationship between the cohomological degree, the dimension of the support, and the depth of the ideal. And a consequence of it is that if the support is too big, then your variety can't be Cohen-Macaulay. Right? And so this would be something that you could check on the composition factors because you know the supports possibly. Right. Finally, a very special situation that we've already seen when you're the affine cone over a smooth projective variety, well, then you have a cone point and you're interested in the multiplicity of this IC in your each local cohomology module. And it turns out that this is determined by differences of de Rham-Betty numbers of the smooth projective variety. And this has been proven in various guises over the years. So I hope I've convinced you that these guys are an interesting invariant of singularities. But then I'm going to tell you more, is that there's all of this stuff is in some sense a shadow of a deeper structure, that of this mixed Hodge module I mentioned. And this is a theory introduced by Saito in 1989. And it's a vast generalization of classical Hodge theory. So in classical Hodge theory, you're interested in the de Rham cohomology of, say, a smooth projective variety. And this de Rham cohomology has a Hodge decomposition, which we call a pure Hodge structure. And then later, the mixed Hodge theory was developed for singular varieties and non-compact varieties, and in which case your de Rham cohomology has two filtrations on it, the Hodge and the weight filtration. And what Saito did was he came along and packaged all of this into the theory of D modules via the Riemann-Hilbert correspondence. Okay, but so the main takeaway for us is that each local cohomology module has two interesting filtrations on it, increasing filtrations. The first of which is called the Hodge filtration, which is usually denoted F, and it's an infinite increasing filtration by finitely generated S modules. So these guys aren't finitely generated over S, but we're going to filter them by finitely generated things. And what is it? It's so in the theory of D modules, there's a notion of good filtration, which is a filtration that you would use to test for holonomicity. And such filtrations aren't unique. They're all essentially cofinal. And what this Hodge filtration is some functorial choice of good filtration coming from complex geometry. The second of which is the weight filtration. And it's a finite filtration by holonomic D modules. And so as we know in algebra, we know that Jordan-Holder filtrations aren't necessarily unique. This is a functorial choice of such. And where do they come from? Well, you get them via log resolutions. So you start with your variety and you apply iterative blow-ups to singular loci. And eventually you end up with a simple normal crossing divisor. So this is a divisor upstairs that locally looks like a union of coordinate planes. And there, the two filtrations are understood. You have what's called a logarithmic de Rham complex, and it has these two natural filtrations on it, and you push those down, and that's how you get these. So that's a definition. That's not how you're going to get them in practice. You should think that Saito proved they exist, and they satisfy nice functorial properties. Here's a first example is the non-singular case where we can tell you exactly what it is. So in the non-singular case, remember there's only one HC and he's simple, and the simple has weight n plus c, where n is the number of variables, c is the codimension. The Hodge filtration is also easy to describe as the elements that are killed, the pth guys, the guys that are killed by the pth plus first power of I. Equivalently, it's the image. So I didn't tell you local cohomology is a limit of x of powers, and so in the case of HC, this guy is the same thing as the image of x of the pth plus first power of I. Questions about this slide? So the power in the theory comes from, so now we're talking about arbitrary variety, not just singular. Or non-singular, the power in the theory comes from comparing the X filtration to the Hodge. So let me write EJP for the image of XJ of IP plus 1, and FJP to be the piece of the Hodge filtration on HJ. I can tell you a bunch of things in the complete intersection case, where from the check complex description, we have a very concrete description of this module. Well, it turns out that the Hodge is always contained in the X for all P. And this was proven by Saito in the case of hypersurfaces, and Musatsa and Popa in the more general complete intersection case. Actually, they were globally more with local cohomology sheaves that are locally complete intersections. But I'm just going to stay in the affine setting and talk about complete intersections. But so the Hodge is always contained in the X. And the difference measures the singularity in the following sense. You're non-singular if and only if the two filtrations coincide. So a converse holds to the example on the previous slide. So in particular, while the D module structure can't tell the difference between a complete intersection and a smooth thing, the Hodge filtration can. Okay. It can also detect rational singularities. So if they coincide for one step, then you can tell that your variety has rational singularities. These are some cohomologically defined type of singularities that mean they're normal, Cohen-Macaulay, etc. But so the 16 is the hypersurface case. The 23 is the more general case. Okay, so this is what this is some info in the complete intersection case. We're not in this bubble. We're not necessarily talking about complete intersections. We're talking about Dubois singularities. So this is some type of singularities coming from Hodge theory that I'll say more about on the next slide. But when you have Dubois singularities, that implies that the Hodge is equal to X in all cohomological degrees for arbitrary I, ideal I. And furthermore, the natural map from X of the first power is an inclusion. Okay, this was proven via different methods by Ma, Schweid, and Shimamoto in 2017, and answers a question of Eisenbud, Mustata, Stillman in the case of Dubois singularities. They ask, when is this natural map an injection? The answer is, or one answer is, if you have Dubois, then X includes, and the image is equal to the Hodge 0. Questions about this slide? Okay. So that's a taste. Let me briefly mention some newer types of mild singularities that have been studied recently in algebraic geometry, but there's connections to this local cohomology. So generalizing the notion of Dubois singularity, you can talk about higher Dubois singularity. So K Dubois, 0 Dubois means Dubois. And you say that your K Dubois, if well, there's a natural map from P forms on Z, the sheaf of P forms on Z, to what's called the Pth graded piece of the Dubois complex for K steps. Okay, what does this have to do with local cohomology? Well, it turns out that these graded pieces that I'm not going to define are actually come from local cohomology due to a result of Saito. So here I'm working in the global setting. Z is some subvariety of a smooth X. And you could look at local cohomology in the derived category. And there's a notion of polynomic duality for D modules. You dualize. And then there's something called the de Rham functor, which you basically take the de Rham complex on X and you twist it by this object. And now this thing inherits a Hodge structure from the Hodge structure on local cohomology. And certain graded pieces give you the graded Dubois. But anyways, it turns out in the complete intersection case, using this machinery, that K Dubois is equivalent to the Hodge equaling the X for K steps. So there's these singularities in algebraic geometry, mild. You should think of them as very mild singularities that comparing Hodge and X can detect for complete intersections. And very briefly, I don't want to get, there's also a notion of higher rational singularities defined in 2023, generalizing the definition of rational singularities from a resolution of singularities. And instead of being related to the de Rham of the dual, it's related to the de Rham of just local cohomology. And it turns out that that in the complete intersection case, being K rational is not equivalent to the Hodge equaling the X, but the Hodge equaling the X on a particular weight piece. Okay, and this is the weight piece that has the IC of I in it. Okay. Anyways, so this is some different ways that the Hodge can and the weights can detect very mild singularities. The Olano paper from 2022 does the hypersurface case, and then Chendricks Musatsa do the complete intersection case. Okay. But anyways, if none of this made any sense to you, that's okay. You can come back now. We're not going to talk about it anymore. But there do remain problems in the non-complete intersection case, foundational problems. First of all, it's not even known in the non-complete intersection case if the Hodge is contained in the X. Okay, this is an open problem, and then we don't even know how to compare them, right? Hopefully these bullet points about K rational K Dubois generalize, but we don't know. Okay, now, I mean, the reason the complete intersection case is a little more straightforward is because this derived thing just becomes a single module, right? But anyways, these open problems are the subject of, there's an AIM workshop this fall on these questions and more surrounding higher Dubois and higher rational singularities. Anyways, so what we want to know more about the non-complete intersection case. And what I want to calculate examples in the non-complete intersection case. And so let me tell you about a leading example for local cohomology for non-complete intersections. I already showed you a couple examples of special cases, namely the determinantal ideals. So we're talking about space of rectangular matrices and the ideal of T by T minors. And almost everything you could possibly want to know is known. All right. So first of all, there's explicit formulas for the composition factors of D modules, which simples appear and with what multiplicity. And furthermore, there's a group action by row and column operations on the space of matrices that preserves the determinantal ideals. And so everything in sight is a representation. And Raiku, Wayman, and Witt figured out the representation structure of local cohomology. Okay, and so the paper from 14 is the maximal minors case. The paper from 16 is the general case. Okay. And then also we know the exfiltration, which is what we want to compare to the Hodge. Okay. All right, and maybe you're not satisfied with knowing the composition factors. Maybe you want to know the submodule lattice, the extensions between the simples. Right, so because, I mean, okay, let's say you wanted to calculate Lubeznik numbers, which are defined in terms of compositions of local cohomology functors. You want to know the submodule lattice. So, Lawrence and Walther, they studied the structure of the relevant category and classified all possible extensions. And then Lawrence and Raiku, they use this to find the submodule lattice in the Lubeznik numbers. All right, and then in more recent work, we figured out the Hodge and the weight filtration, the Hodge filtration in terms of representation. And as an application, we find the Hodge ideals, which are certain ideals that appear in the hypersurface case for the determinant hypersurface. And then in more recent work, with Deba Ray Chowdhury, we show that indeed the answer to the open question on the previous slide is affirmative in the case of determinantal varieties. The Hodge filtration is always contained in the X, and we can actually say when it's an equality. Right, so we expect that determinantal varieties are 1 Dubois, but not 2 Dubois. Okay, but this is open, this is active, we're working on this right now. Okay. But anyways, what I'm trying to illustrate is that everything you could possibly want to know is known. Okay. And say very few words about some of the techniques that go into these results. The umbrella term I would just use is the theory of equivariant D modules. Okay, the idea is that D modules in representation theory go together like spaghetti and meatballs, right? So the group action gives you a very nice stratification by the orbits. So the orbits are the rank of the matrix of this group action, and it gives you what's called a Whitney stratification, which is a nice stratification that is integral to the theory of perverse sheaves, which are equivalent to D modules. But anyways, it gives you the perfect playground for playing with these things. And it gives you a plethora of tools for classifying simple all the simples that you could possibly care about, classifying the extensions, this item about the structure of the category. If your group is sufficiently nice, your category is equivalent to a quiver with relations, etc. And then once you have that toolbox, you also have the Borel-Weber theory. So your varieties have very nice desingularizations by vector bundles on flag varieties, and you can push things down that you might care about using Borel-Weber theorem, which is a result that tells you how to calculate cohomology of vector bundles on flag varieties. Okay, but anyways, what we're trying to do is take these techniques that have been successful for determinantal varieties and develop them and apply them to other varieties with large groups of symmetry. So here's a cartoon of some various directions where we're advancing from ground zero, being determinantal varieties. So this black arrow relation is a subset relation. So determinantal varieties are an example of what's called quiver loci. So you start with a quiver and you attach a vertex to you attach a vector space to each vertex and a linear map to each arrow. And then you act by change of bases on the vertices and you get some orbits. And you can study the geometry of the orbit closures. And the determinantal varieties are examples of orbit or quiver loci in the A2 quiver. But anyways, we'd like to apply these techniques to such loci. There's these things I'll call, for the sake of this talk, Windberg varieties. There's been a lot of work on these guys recently. So in the case of determinantal varieties, the space of matrices is an irreducible representation of the relevant group. And a Windberg variety is an orbit closure in an irreducible representation of a reductive group. And there's a nice classification of such things. And there's been quite a lot of work done for D modules on such things. Okay. Another direction you could go, and what I'm going to tell you about in the second part of my talk, is about Schubert varieties. So determinantal varieties are some special open subsets of Schubert varieties. And we'd like to run the board and answer all the questions on the previous slide for Schubert's. Okay. And then the pie in the sky would be to do these things for spherical varieties, toric varieties, nilpotent orbit closures, and maybe come up with a totally uniform method to attack spherical varieties, for example. But anyways, I think this is a good place to pause for a break.
Okay, should we regroup in 4 minutes? Is that a long enough break? Yeah, so we'll restart in 4 minutes. Yeah, 45.
Nice exposition.
Oh, thank you.
I think I once asked Mircea at an Oberwolfach meeting to explain what he had just spoken about in Hodge modules, and he said it's impossible.
No.
Michael?
Now let's do it. All right. So the second half of the talk will be a little disjoint in the sense that I'm really just going to be focused on not on the Hodge filtration. But so if you didn't like any of the Hodge stuff I was talking about, you can come back now. And I talk about Schubert varieties. So I'm not going to talk generally for going forward. Eventually, I'll just talk about the Grassmannian. But so Schubert varieties are some special subvarieties of what's called the generalized flag variety. So here, G is a simple Lie group like SL or SP or SO, and P is what's called a parabolic subgroup, such as the Borel subgroup of upper triangular matrices. If this means nothing to you, you can think about the Grassmannian or a complete flag variety. And ZW is some subvariety defined by natural linear algebraic conditions. They fit into the scheme from the previous slide in the sense that they're orbit closures. There's an action by the Borel subgroup, giving the Schubert stratification, and these are the orbit closures. Right, but these are a good place to test some conjectures about these mild singularities I was talking about, because many different singularity types appear here, and there's a whole industry in combinatorics and algebraic geometry interested in studying these things. And there's a textbook account by Billy and Lakshmibai from 2000. Right, but the general rule of thumb is that cohomological objects associated with Schubert varieties are important. And here's a list of the first 5 things that came to my mind when I was writing this slide. For example, in combinatorics, the Schubert polynomials are some polynomials that come from the cohomology classes of Schubert varieties in the Chow ring of flag variety, or the Kazhdan Lusztig polynomials, which will come up later, which are in some they're the generating functions of the intersection cohomology of Schubert varieties. And then there's the Littlewood-Richardson rule, which is describes the cup product in the cohomology ring of the Grassmannian. So, I mean, and all of that goes together to Schubert calculus and algebraic geometry, which is the, I'll describe it as the study of the cohomology ring of the Grassmannian in effort to study enumerative problems. And then representation theory loved these things, especially D modules on Schubert varieties, which are used to describe composition factors of Verma modules over Lie algebras. This is going to come back later. And then in more recent work, they've used mixed Hodge modules on Schubert varieties to test representations of real Lie groups, namely to test when they're unitary, when they land in the unitary group. Okay, but anyways, so one problem that remains open is to calculate the local cohomology with support in a Schubert variety. And I've done a bit of a bait and switch on you in the sense that now I'm in the global setting. So now I'm working with local cohomology sheaves, which locally satisfy everything that I've told you so far. And so they have a Hodge filtration and a weight filtration. Oh, but what's D? D is now the sheaf of differential operators, which locally looks like the Weil algebra. And so one would like to calculate the composition factors, the Hodge filtration, the weight filtration. And then, okay, we want to take global sections also. And I'm not going to talk about this global sections guy any further, because there's a special theorem in the case of flag varieties called the Beilinson-Bernstein theorem, which says that global sections is exact. And so in particular, knowing the composition factors of the sheafy guy is the same as knowing the structure of the vector space guy. Right, and then so I'll paraphrase. Oh, so let me. I'm getting ahead of myself. So okay, what do I mean? I want to know the multiplicity of an intersection cohomology module associated to a smaller Schubert variety inside the local cohomology with support in ZW. Okay, by the general theory, these are the only guys that could show up. This is a bit of overkill, but it follows from equivariance. Due to the presence of this special group action, and the fact that the orbits are affine spaces, these are the only composition factors that could show up. And so we want to know the multiplicity. Okay, and I paraphrase the main result is that I outline a general strategy for a Schubert variety in any complete flag or generalized flag variety, and its weight filtration. I don't quite have any. I don't have a. I mean, I'll say more about the Hodge filtration later. But the idea is to use the theory of mixed Hodge modules and what's called Kazhdan-Lusztig theory, which my definition of Kazhdan-Lusztig theory is the study of composition factors of Verma modules. So I'll tell you about that later. So I provide some general strategy and I execute it in the case of the Grassmannian. Okay, and that's what we're going to talk about for the rest of the talk. As an application, I mentioned that there's there's some special open subset of the Grassmannian called the opposite big cell. And certain Schubert varieties restrict on the opposite big cell to the determinantal varieties. And so we recover the example of composition factors and weight filtration for determinantal varieties. So let's dive into the Grassmannian. So for me, going forward, X is going to be the Grassmannian of k-dimensional subspaces of an n-dimensional vector space V, which is a nice smooth projective variety of dimension k times n minus k. And once and for all, I'm going to fix a complete flag of vector subspaces. So here Vi is a fixed subspace of dimension I. And the Schubert varieties are some subvarieties defined by these linear algebraic conditions. So let's break it down a little bit. So I want to start with a partition A, which I'm going to identify with its Young diagram. So the partition 5331 gets identified with the left justified collection of boxes 5331. And I only want to look at Young diagrams satisfying this property, namely, I have at most k rows, and I have at most n minus k columns. So my Young diagrams fit inside of a k by n minus k rectangle. Okay. And to such a Young diagram, you can associate a Schubert variety, and it's defined to be the subspaces of V that intersect your flag in this prescribed way. You have some lower bounds on the dimensions of the intersections of W with certain pieces of your fixed flag. Okay. If you've never seen this before, this definition isn't going to be very illuminating. I'll do an example on the next slide by doing examples. This is the kind of thing that's done in the privacy of your own home. Two basic examples are the case when you have the zero partition. If you take the zero partition, 0, 0, 0, and you unpack the definition, you get the subspaces of dimension k that intersect Vj in dimension at most, or at least j, right? So there's only one guy that satisfies this property, and it's the kth guy in your fixed flag, right? So Z0 is a single point in your flag variety. On the other end of the spectrum, if you look at the partition that's the whole rectangle, the k by n minus k rectangle, you get the whole Grassmannian. And this comes from general bounds on the dimensions of sums of subspaces and intersections of subspaces. You get the whole thing. Anyways, so my convention here is that bigger Young diagrams correspond to bigger Schubert varieties. So in particular, the dimension of ZA is the number of boxes in the Young diagram. And one Schubert variety is contained in the other if and only if their Young diagrams are contained in each other. So BI is less than or equal to AI for all I. So that's consistent with 0 being the smallest and this being the biggest, right? So here's the smallest example that is not projective space. G24, two-dimensional subspaces of a four-dimensional vector space. So everything fits inside of a 2 by 2 rectangle. And so we have a single Schubert divisor, Z21, which is the guys that intersect our fixed two-dimensional subspace non-trivially. And this guy has two subvarieties of codimension 1, namely 1, 1, and 2. And these are the ones that, in addition, well, one of one is contained in V3, and the other one contains V1. And of course, containing V1 implies that you intersect V2 non-trivially. If you intersect these two, you get the W's that fit between. Well, this guy is a projective space, right? It's a P1, right? It's the one-dimensional subspaces of V3 mod V1. So this guy is smooth. And then it has the single point inside of it, which is V2, which of course fits in the middle. So this is the Schubert stratification on G24. Questions about any Schubert stuff? Okay, so I want to know local cohomology with support in these guys. Well, I should probably first tell you what is the singular locus. Okay. So this is a result of Lakshmibai and Wayman from 1990, and it's a description in terms of the Young diagram. So the singular locus will be a union of some sub-Schubert varieties, and it's a union of those obtained by removing hooks, I'll call them, from A. And so the idea is, well, here's A is 4, 3, 3, 1, and you look at the two indentations. You have an inside corner here, and you have an inside corner here. Okay, you can get 4, 3 by removing the hook surrounding the bottom indentation, and you can get 2, 2, 2, 1 by removing the hook surrounding the top indentation. So this is the singular locus. In particular, we have a complete classification of non-singular Schubert varieties. Your Schubert variety is non-singular if and only if you started with a rectangle to begin with, when you have no indentations, right? So in particular, we can already completely describe local cohomology for rectangular partitions, right? By what we know about local cohomology in the non-singular case, we know that the codimension one is simple and all others vanish. Okay. And in the following slides, I'm going to tell you a combinatorial rule for how to remove even more from your Young diagram. So I want to start with this notion of what's called a Dick path, which these Dick paths have been studied in combinatorics. I couldn't even, I mean, it goes back to at least the 80s. One particular case they appear is they enumerate Kazhdan numbers. The number of Dick paths of a given length is a Kazhdan number. But in the work of Brenti is the first place, as far as I can tell, they appear in the context of Schubert varieties. And so what are they? They're some connected collection of boxes inside your Young diagram, obtained by walking a combination of north and east. So I want to start down here and go upright, upright. And the rule is I want to start and end on the same anti-diagonal. So they're collinear on an anti-diagonal. And I never want to walk below that fixed anti-diagonal. So here I start, I go upright, upright, and I end, but I never went below. But here I went too far to the right. This box is not admissible. So this is a non-example. This one is perfectly valid too. I don't have to, I can zigzag any way I want. And a path of length 1 is perfectly valid. This one is bad because it fails the second bullet point. It doesn't start and end on the same anti-diagonal. Questions about Dick path before I go on? So observe that the hooks on this previous slide are not Dick paths. They go too, this one goes too far to the right, and this one doesn't end, this one ends too high. Okay, so what I'm going to do is I'm going to augment my Dick paths. So what I want to do is I want to start with the Dick path, and I want to add these green dots called bullets emanating from the head and the tail. Okay? And if you think about the definition of a Dick path, every Dick path must start by going up, and it must end by going to the right. And what I want to do is I want to fill in the boxes all the way to the edge going right and all the way down to the edge going down And I want to color them in this green color. Okay, and call them bullets. Okay, and now notice that the hooks I was talking about for the singular locus can be represented by augmented dict paths, okay? Possibly in multiple ways. All right, and what I want to do is I want to remove these in a coherent fashion, and this is the definition due to Raiku and Wayman in a totally different setting, namely in the setting of syzygies, particularly syzygies of determinantal thickenings, these equivariant scheme theoretic thickenings of determinantal ideals. And it turns out that these augmented dict patterns control the linear strands of such ideals. And towards the end, I'll explain why, what the connection is. But anyways, it's a lot on the slide. It's some collection of augmented dict paths satisfying a couple properties. The first of which is that I want all of my dict paths to be length at least 3. And if you think about the definition of dict path, they must all have odd length. So I'm only omitting dict paths of length 1. Okay, and dict paths of length 1 will come up later. Okay, and then the key condition is this covering condition, which says that if you have one dict path to the left of another, it must totally overlap it. So this one totally overlaps this one. This one totally overlaps this one. However, this one does not totally overlap this one. So in symbols, if the left one touches the right one to the north, northwest, or west, then every box north, northwest, or west of the right one belongs to the left one. I call this the covering condition. Okay, and then okay, in the end of the day, I want to end up with a partition. So this is I want the complement of the pattern to be a partition, and in all 4 pictures here, the complement is a partition. Okay. Questions about the definition?
In the examples, you have a dict path of length 1.
Oh, thank you. It's because I made a last-minute change in my definition to not include dict paths of length 1. Anyways, okay. For the purposes of this slide, this is also a non-example. Thank you, Claudio. Okay, so here, yeah, so you see the remnants of, I insist they all have length at least 3. So here are 2 examples of augmented dict patterns. One for A is 5, 3, 2. You can cover the indentation with this path of length 3, or you can cover this indentation, but you need to augment it if you want the complement to be a partition. Or you can zigzag, but then you also need to augment it if you want a partition because you can't go further to the right. Okay, and then you can cover this guy, but you can't go any further to the right, so you must augment. And so these are the only things you can do in this particular example. In this case, I only have one divot, and the only thing I could do is cover the divot with a path of length 3. And then after that, all I could do is cover that completely if I want to satisfy the covering condition. And then if I want to add another one, I must cover completely. And that's all I can do. Questions about the patterns on this slide? Good. Okay, so here's the theorem on composition factors for Grassmannian. So I start with some Schubert variety in the Grassmannian associated to a Young diagram A. And I'm interested in the composition factors. Well, we know that HC, the codimension, is the first non-zero one. So let's just start counting at the codimension spot. And I want to know the multiplicity of the intersection cohomology module of B, ZB. And it turns out that that it's determined by these augmented dict patterns. So I want B to be obtained from A by removing an augmented Dick pattern, where all paths have length at least 3. And I want, so here's where the cohomological degree comes in. I want Q to be the number of bullets, Q to be the number of green circles. Okay, so that tells you everything you could possibly want to know about the composition factors. And then the weight filtration is determined. I'm sweeping the exact numerology under the rug, but the weight filtration is determined by the number of paths plus the number of bullets in the diagram. So continuing that example from the previous slide, if we're interested in 532 in the Grassmannian of 3-dimensional subspaces of an 8-dimensional vector space, it has codimension 5 because we're missing 5 boxes. We discussed on the previous slide why these are the only things you can do. And so I write in the growth and group. So it's plus means these are the composition factors. So H5, the codimension, has 2 composition factors coming from the fact that these guys both have no bullets, 532 and 511. H6 is L222 plus L211 because both of these have 1 bullet. And then this last guy is the simple supported on the 0-dimensional Schubert variety. And then the weight filtration is the number of paths plus the number of bullets. So then this guy would live in weight 0, and this guy would live in weight 1. Okay. Both of these have the same weight. They both live in weight 2. And then this guy has weight 4. Questions about the statement of the theorem or this example? Okay. Here's a bigger example just to show you what else could happen. So these are, we're looking at 5422 and G49, which has codimension 7 because we're missing 7 boxes. And in this case, I just want to point out, okay, H7 will have 4 composition factors in this case because there's 4 patterns with no bullets. And then so this guy would have weight 0, and the other 3 would all have weight 1. Right. Bigger example for good measure. So what about this, well, I already told you about the smooth case. So what about the rationally smooth case? So I told you that a Schubert variety is smooth if and only if your A is a rectangle of some size. Okay, but if you think about it, that's the case when you have no indentations. So that's equivalent to you admitting no Dick patterns where all the paths have length at least 3. So in particular, you have no more composition factors. So what it turns out to happen is that this rational smoothness condition that I told you about is equivalent to smoothness. And this was already known to the combinatorialists in the 90s by other means. What about the hypersurface case? So we always have one Schubert divisor. The one Schubert divisor is given by removing a single box. And as we saw in a previous slide, there's only one way to remove Dick patterns from this picture. This is a cartoon for all Schubert divisors. And so we see that there's no bullets. And so there's always only going to be H1. Okay. And so these are the compositions of H1, and the weight filtration is given by the number of paths. Questions about this slide? Okay, so I'm a bit low on time. Let me briefly tell you about the determinantal case. So I told you that for determinantal varieties, the composition factors and the weight filtration are already known. But we can recover these results by restricting to a certain open subset. So there's a special open subset of the Grassmannian called the opposite big cell. Basically, what you do is you take the opposite flag by whatever basis you chose for your fixed flag. You reverse the order of the basis, and you get the opposite flag. And you could talk about Schubert cells with respect to that flag, and then you get the opposite big cell. And you can identify it with an n times n dimensional affine space. So in particular, you can identify it with the space of matrices in this particular Grassmannian. And certain Schubert varieties restrict to the determinantal varieties. So here, YP is matrices of rank at most P. And really what you do is you start with the complete rectangle and you remove a rectangle of size n minus p by n minus p from the bottom right. So in G48, well, this corresponds to matrices of full rank, which is dense. This is the determinant hypersurface. Matrices of rank at most 2, at most 1, and the zero matrix. Okay. And so then we can apply the combinatorial rule to recover the composition factors, in particular, the example we saw on an earlier slide. So if you look at the 3x3 minors of a 4x4 matrix, you're starting with this diagram, and all you can really do is remove hook shapes in the shape of an augmented Dick path. Okay, so if you only remove paths with no bullets, you get the codimension 4 guy and its composition factors. Or you can remove 2 bullets and get these 2, or you can remove 4 and get this one. Okay, so this is how one could recover the composition factors and weight filtration for determinantal. Questions about this slide? All right, so I owe you some words about the proof. It's not magic. It follows from some very heavy machinery from representation theory in the 80s. The first of which is what's called the localization theorem, which I paraphrase here. So these next 2 slides hold equally well for any flag variety, but for simplicity, I'm only going to talk about Grassmannian. Okay, so you can replace Grassmannian with your favorite flag variety and your favorite Lie algebra. So a consequence of what Bailenson and Bernstein show is that they show that the global sections functor is exact on the category of D modules on the Grassmannian, and you get modules over the corresponding Lie algebra. Okay. And furthermore, they show an equivalence of categories with certain highest weight modules over your Lie algebra. And a key player in the theory is local cohomology with support in a Schubert cell, which is something we have yet to talk about. So what you can do is you can look at the orbits, the Borel orbits, which are called Schubert cells. And instead of looking at local cohomology with support in their closure, you look at local cohomology with support in the cell. These are affine spaces. And so there's only the codimension guy. And of special interest to representation theorists is the global sections of the dual, polynomic dual of this guy. And it goes by the name of a parabolic Verma module. So these are some special modules of GL that are induced from the parabolic subgroup or subalgebra that you care about. And then if you take global sections of the IC, you get simple representations. And by the dual of this IC fact I told you, you get the simple quotient of the parabolic Verma module. Okay, and these are some highest weights. I'm obscuring what the weights are, but they correspond to our partitions in the Grassmannian case. Okay, so what is the Kazhdan-Lusztig theorem? Is a way to find the multiplicity of the composition factors, and so I'm not going to. So Kazhdan-Lusztig polynomials are some polynomials arising from combinatorics. You start with some Hecke algebra corresponding to your Weil group And a natural change of basis gives you, that I don't know a lot about, gives you these things called Kazhdan Lusztig polynomials that have integral coefficients. But what the Kazhdan Lusztig theorem says, which is due to Beilinson and Bernstein and independently by Belinsky and Kashiwara, is that if you evaluate your KL polynomial at 1, that tells you what the multiplicity is as a composition factor. And this is what they were interested in, because in rep theory, they were interested in the character of this simple. And it's easy to get the character of the Verma. So once you know this formula, you can extract the character of the simple from this formula. Okay. This next bullet point you could think of as the definition of the KL polynomial. And it's honestly how I think of the definition of the KL polynomial. And what it is it's the generating function for the weight filtration. So these parabolic Verma modules have a weight filtration, and you can look at the generating function for the multiplicity of LB in the jth weighted piece. And that's what up to a shift in some enumerative changes. I paraphrase here, but that's what the Kazhdan Lusztig polynomial is. Okay. And in general, these Kazhdan Lusztig polynomials are very difficult to describe, and they're described by recursive procedure. Okay, but one thing that works for us is in the Grassmannian case, the one we've been talking about for the last few minutes. There's a very concrete description of the coefficients in terms of these Dick patterns. But when I say Dick pattern, I don't mean augmented Dick pattern in the sense of Raiku-Weyman. I mean a Dick pattern satisfying the covering condition, but there's no bullets. So you're not augmenting your paths at all. And you're also allowing paths of length 1. Okay. Questions about this slide? So a lot is known about these guys. What does it have to do with the guys that I care about, the local cohomology with support in the closed? Well, there's a special complex called the Grothendieck-Cousin complex, which was introduced by Kempf, also in the study of finding character formula for these simples in representation theory. And what Kempf shows, well, in the category of OX modules, but it follows in the category of D modules, that the structure sheaf admits a right resolution by Verma modules. So what you do is you look at direct sums of Schuberts of various codimensions. Okay. And so this is a right resolution, and so you could use it to calculate local cohomology, if you will, but that's not what Kempf was interested in. But the main reason that this works is because the Schuberts, like I said, are affine. And the occlusion of a Schubert into a flag is an affine morphism. And that's what makes this complex exist. Such a complex doesn't exist for an arbitrary stratification. Okay. But what you can do, again, using affineness, is you can take this resolution and apply the sections with support functor. Okay, and by affineness, I call this regular GC. You get the Vermas where the B's are contained in the A you care about. So everything that isn't supported in A goes away. Okay? And then again, by affineness and the fact that this is a resolution, you can calculate the cohomology we care about as the Qth cohomology of this GCA, in theory, if you know the composition factors of the Verma. And so what I show is that this isn't, and this isn't too hard of a proof from the general theory, is that this GCA isn't just a complex of D modules, it's a complex of mixed Hodge modules. In particular, it's endowed with these two filtrations. And so the category of mixed Hodge modules is an abelian category, but furthermore, morphisms are strict with respect to the Hodge and weight filtration. And what that means is that cohomology commutes with associated graded. So in fancy terms, the spectral sequence of the filtered complex degenerates at the E1, okay? But anyways, if you know the composition factors and you know the submodule lattice of the Verma, which is really only known for the Grassmannian case, you can calculate the cohomology of, you can calculate the weight filtration. The Hodge filtration, they don't know, as far as I can tell, they don't know the Hodge filtration on a Verma. So if you did know the Hodge filtration on a Verma, you could, in theory, get it. Okay. What does this have to do with syzygies of determinantal thickenings? Well, there's something called superduality, which relates representations of Lie algebras with Lie superalgebra, GL, MN. And this complex, in fact, gets, via the BGG theorem, it gets related to the complex that calculates the linear strands of syzygies of determinantal thickenings, which were calculated by Amy Huang. Okay. So what I would like to do going forward is figure out the Hodge from the Hodge on the Verma, if possible, and then also do this for other Lie types where the KL polynomials are accessible. So I end with a conjectural example of a symplectic Grassmannian, a Schubert varietyness symplectic Grassmannian, where Brenty defined these, he calls them shifted Dick patterns, where they don't have to start and end on the same diagonal, but if they don't, you have to add this extra info. Okay, and then but his didn't have any augmentation by bullets. And conjecturally, I have a description where you augment them in an analogous way to the Grassmannian case, and you can also get the composition factors. But this example is conjectural at this point. Anyways, this is where I'll stop.
Let's thank our speaker. I think there's time for a question or two. If anybody wants to unmute themselves and ask away. Or put it in the chat and I can ask it.
So do you know anything about some ends of these local cohomology modules? Or which ones are indecomposable, which ones split up?
Yeah, so, well, conjecturally, but I haven't been able to prove it. So the idea is, well, in the determinantal case, as Claudio knows, but maybe the audience doesn't, is the indecomposable summands are known. And in this picture, they're not bad to describe. They're given by whether the Dick patterns are nested in each other or not. Notice that this one is nested in this one, and this one is also, this one subsumes this one. And so you would expect there to be a non-trivial extension, and a non-trivial extension here to here. Now on this other example, so you would also expect these also to be non-trivial extensions because they're nested. On this slide, so while all three of these are in the same local cohomology module because they have no bullets, they're not nested. So you would expect there to be no non-trivial extensions between these three guys. Okay. And I guess in this case, it's proven because they all have the same weight. And since they all have the same weight, there can't be an extension. Good question, thank you.
But the simple depends only on the underlying partition, no?
Correct.
So you're saying that there's whether they can form an extension is whether there is a way to fill in the difference by these nested things. That's what you're saying.
Exactly. Conjecturally. And okay, yeah, I mean, if you could prove this, then you could recover it for determinantal varieties and also prove it for other classes like symmetric determinantal varieties and Pfaffian.
There's another question in the chat. Can anything be said about degeneracy loci? I think the idea is we replace the Schubert guys with more general degeneracy loci.
I don't know. Yeah, I mean, I guess you would need your everything to be sufficiently generic. And yeah, I guess I don't know. I admit I haven't read this paper, but there was a paper written recently by Nero Badur and somebody else where they studied degeneracy loci, and some of these calculations come up. But I can't speak to it.
So if you look at the maybe general flag varieties and just focus on a divisor, can you tell something about the length of local cohomology?
I mean, the tough thing is that I get the non-recursive nature, or the recursive nature of the Kazhdan Lusztig polynomials in the complete flag case, and also your Verma modules are no longer multiplicity free, so things become more complicated. And so, I mean, maybe I could come up with a recursive procedure to find the composition factors in the divisor case, but I don't expect any sort of closed formula, except in this co-minuscule case that I've been talking about.
Don't hear any other questions. Maybe we can give one more round of applause.
Thank
Yeah,
you.
thanks for coming, and thanks again for the invitation.
Thank you.
All right. Greg, you got my email? Yes?
I did. Yep.
All right. All right. I'm supposed to
All
see
right.
I have this this membership to AMC, so I could see unlimited